Good afternoon, everyone. I'm Bobby Schnabel, the External Chair of the Computer Science Department at CU Boulder. It's a pleasure to welcome all of you to this webinar, which is part of our celebration of the 50th anniversary of the Computer Science Department. We already have, over 200 people who've joined us, including CU students, faculty and staff, alumni, tech community members, and more. We're delighted to have you all here. Thanks so much for joining us. I should mention that a number of you submitted questions with your registration. You can also enter them in that thing that says Q&A right under the webinar at any time during the webinar. I should also apologize in advance that we already have considerably more questions than we'll get to, so sorry if we don't get to yours. We're delighted to have with us today Professor Tammy Sumner, Professor of Computer Science, Director of the Institute of Cognitive Science, and a two-time CU alum, and former CU Boulder Computer Science and Institute of Cognitive Science professors Mike Mosier and Paul Smolensky, both of whom, as you know, are world-leading researchers in neural nets and deep learning. And with that, I'll turn it over to Tammy, who will moderate.
Thank you, Bobby. It is very fitting that this 50th anniversary series is launched with a panel on neural networks and deep learning. CU Boulder played a critical role in nurturing this field through our early faculty investments in neural networks and their applications to cognitive science research. This was enabled by the long-standing partnership between the Department of Computer Science and the Institute of Computer Science, and this partnership enabled us to successfully recruit Professors Moser and Smolensky, our speakers today, and to create a unique space that allowed their cutting edge and interdisciplinary research to grow and flourish. So without further ado, I'm going to briefly introduce our panelists and then we can begin. Michael Moser served for 30 years as a professor in the Department of Computer Science and the Institute of Cognitive Science. He recently joined Google Brain as a research scientist. Mike is also the secretary of the Neural Information Processing Systems Foundation and a former chair of the Cognitive Science Society. Mike is interested in human-centric artificial intelligence. This involves designing machine learning methods that leverage insights from human cognition and building machine learning-based software tools that help people better learn, remember, and make decisions. Paul Smolensky was a professor in the Department of Computer Science and the Institute of Cognitive Science here at CU Boulder for 9 years before joining Johns Hopkins University in 1994, where he was a professor in their Department of Cognitive Science. Since 2016, he has also served as a partner researcher in the deep learning group at Microsoft Research. Paul's research has pursued the unification of symbolic and neural computation. For this, he received the 5th David E. Rumelhart Prize for outstanding contributions to the formal analysis of human cognition. So congratulations, Paul. Okay, with that, Mike and Paul are going to kick off our discussion with a short presentation.
I am going to go first. Is my screen visible to the world? Awesome. And Paul's going to give another presentation. We're aiming for about 10 minutes apiece and then spend the rest of the time having a conversation. So I wanted to go back. I know there's some people in the audience who don't have a background and know the whole history of this field. And so I just wanted to start by going way back to the earliest days of neural networks. And I made a timeline here to anchor the major events. And I want to start back in a year that, well, it was particularly significant to me. It was my birth year. It was also the year that Frank Rosenblatt wrote an article in Psychological Review. Rosenblatt was a psychologist. The article was called The Perceptron, a probabilistic model for information storage and organization in the brain. And for folks who don't have a background in machine learning, this is my one-slide introduction to machine learning. The promise of the algorithm that he proposed, called the perceptron, is that you show the system a set of examples that are labeled as A's and B's or positives and negatives, and you feed it into the system and it comes out and says, yes, that's a positive example, or no, it's not a positive example. And you reward the system when it gets the right answer. And this black box learns to classify A's versus B's from the examples. So it programs itself from examples. The amazing thing in this article, in his research, was that he showed mathematically that a perceptron can learn anything it can be programmed to do. So you don't have to program it by hand, you can let it do learning. That caused lots of excitement in probably the first real wave of excitement in machine learning, until about a decade later, a book appeared by Marvin Minsky and Seymour Papert called Perceptrons that did a really nice theoretical computer science analysis looking at scaling properties and computability. And they showed that there are many things that a perceptron can't learn to do, both in principle and in practice. That killed the field, and there was the first real neural net winter where there wasn't much rationale for working with neural nets because everyone knew that Minsky and Papert had showed their limitations. The only people who were foolish enough to go off and still play around with neural nets were clueless psychologists, including these folks at UC San Diego, Don Norman and Jay McClellan and Dave Rumelhart. And Don, on the left there, is one of the founders of the field of cognitive science, and he hosted the first cognitive science conference at UCSD in 1979. Jay and Dave founded a group called the PDP group. PDP stood for Parallel Distributed Processing. And they decided to look at neural networks as mainly as a psychological model. Is it a reasonable theory of how our cognitive systems work? Their group involved, it became a large group, and they invited postdocs to come out for a few years. Their first postdoc was this fellow named Jeff Hinton. I tried to find old photos of everyone, but that's the oldest one I could find of Jeff. And then a year later, another fellow named Paul Smolenski showed up. And I also started grad school at UCSD at the same time. And the PDP group was very productive during the 80s and built cognitive models, mostly using neural networks, of a bunch of phenomena. And the kind of highlight of the whole era was this paper that came out from Dave Rumelhart and Jeff Hinton and a postdoc named Ron Williams called Learning Representations by Backpropagating Errors. I'm going to actually read you the abstract because I think, again, for folks who, if there's anyone in the audience who doesn't have a machine learning background, it will explain to you a little bit about what's going on. The abstract says, we describe a new learning procedure, backpropagation, for networks of neuron-like units. The procedure repeatedly adjusts the weights of the connections in a network so as to minimize a measure of the difference between the actual output vector of the net and the desired output vector. As a result of the weight adjustments, internal hidden units, which are not part of the input or output, come to represent important features of the task domain, and the regularities in the task are captured by the interactions of these units. The ability to create useful new features distinguishes backpropagation from earlier simple methods, such as the perceptron convergence procedure. So what they showed was they could overcome this sort of fundamental limitation of perceptrons, and that led to another wave of excitement about neural networks. And this time the field was branded as connectionism, in the sense that the knowledge is in the connections among neurons. Many cognitive scientists were excited about this as the Cognitive Science Society got off the ground. The CogSci conference was a hotbed of work in this area. And AI and machine learning people started to get wind of the field as well. And it caught their interest, and many of these machine learning folks were very strong mathematicians, and they developed more principled, mathematically speaking, more principled methods like support vector machines and Bayesian approaches. And neural nets fell out of favor, partly because they weren't the hot thing of the week, but partly because, again, there was some nice theoretical foundations for these other approaches, and neural nets just seemed like a hacker's universe. In the early 2010s, neural nets reappeared. New generation of folks got excited about them. It was branded this time as deep learning, and Jeff Hinton is both the father and the grandfather of deep learning. So what happened in this period of 15 to 20 years between connectionism and deep learning? There was definitely a time in there where neural nets were way out of favor, that if you looked in a machine learning conference, someone did an analysis of what keywords predicted acceptance or rejection of a paper, and the two top keywords that predicted rejection were neural and network. So what happened during this time? Well, among other things, computers got a lot faster, and data sets got a lot larger thanks to the internet, and software tools evolved for doing neural networks. Things like TensorFlow and PyTorch, JAX emerged. And then there's some special sauce, some new insights, methods, and architectures that people developed, in part because there's so many people working in the field now that have really changed the game. Some of these bits of special sauce have to do with a theoretical understanding of why and when overparameterized models generalize well. There are a bunch of new practical tricks to getting deep neural networks with many layers of hidden units to train, and there's new forms of inductive bias and architectural constraints. And I believe Paul is going to focus on one particularly interesting such development that he's made some very important contributions to. And I'll say more too about specific ideas that I think are hot ideas if we circle back. To finish up, I just want to revisit the timeline from a Colorado-centric perspective. And I'm going to jump way back to when Paul arrived in Boulder, I think 1985. He came as an assistant professor in computer science, came from UCSD. His hire, as Tammy mentioned, was encouraged and supported by the Institute of Cognitive Science. In 1988, I came to Boulder as an assistant professor, rostered in Cog Sci with a home department in CS, much to the dismay of real computer scientists. And in 1988, we had the first Neural Information Processing Systems Conference, a conference that was devoted to neural nets for machine learning. It was held in Colorado at the Denver Tech Center. It was a week-long event. There were tutorials, conference, workshops. The workshops were in the mountains and people went skiing, so that the workshops were held from 7 to 10 in the morning and 4 to 7 at night, and people skied during the daytime. In 1993, we, Paul and I and a few other folks, hosted the Connectionist Model Summer School. There were 2 summer schools before ours, and between the 3 of these summer schools, ours was the last. Most of the senior researchers in the field today attended one or the other, either as faculty or as students. I was a student in the '86 summer school. Paul and I had a group called the Boulder Connectionist Research Group. This was us in our heyday. You can see there's Paul on the right, and there's me in front, and Dave Rumelhart was visiting us that time. And I think Patrick Lynn chimed in on chat, and Kevin Markey is also in chat. And apologies if there's others of you who are here. Those are the folks who I know about right now. We had a sort of unique character of the group that did neural networks in Boulder, that we had these very strong connections to cognitive science. Paul was a linguist and philosopher. primarily. Paul's in everything, but he views himself as a linguist and philosopher. Myself, Eliana, Yuko Munakata in psychology, were interested more from a psychological perspective, and Randy O'Reilly more from a neuroscience perspective, but we all had connections between neural nets and cognitive science. We had a group t-shirt, which I'm wearing. It's not just that I'm a slob, even though I am a slob. And I just wanted to explain the t-shirt. So Paul had developed a framework called harmony theory. And like many algorithms in neural networks and machine learning, it involves optimization, finding a maximum of a function. And this function Paul called harmony. And you can see the function is kind of outlined by the peaks of the mountains here. And like many learning methods or neural net methods, a lot of these methods perform local optimization. So they get to a local optimizer and they get stuck there. So we started off with specific universities, but we made it more generic: East Coast, Canada, West Coast, and it's worn off of my shirt, but Boulder's up here on top and there's a little guy climbing the mountains. So that was our official group. And unfortunately, Paul left for new adventures in the mid-90s. And the Neural Information Processing Systems Conference finally moved on from Colorado. I did my best to keep it in Colorado so that students could take the week off and come down to the conference. And then I headed off in 2018. Here I found a couple old posters from the early days of the conference. There is the Colorado mountains in the background. I think I was program chair one of these years, I'm not sure. And just to give you a feel for sort of what's happening in the field, if you aren't paying attention by any chance, here's attendance at Neural Information Processing Systems. Again, there's sort of different registrations for tutorials, conference, and workshops. This is from 2001 to 2020. In 2020, there were 23,500 participants altogether. There's a large number of industry participants, but from the way the registration system is kind of restricted because we have to limit registration, more than half of the industry presenters, more than half of the industry attendees are researchers in industry as well. There's a lot of research going on in industry, as Paul and my affiliations reflect. The conference has over 150 sponsors and press coverage, and we have a year-round PR firm that deals with the press. So the field has gotten super hot, and I'm not sure how long it will last. That would be a good thing to discuss. I don't have an answer, but that's where we're at right now.
And let me throw in that, was it 2019? You may remember, the registration was online, and people were warned that it was probably going to fill up, so you probably don't want to delay. And the entire conference sold out in 11.5 minutes.
Yeah, we caught a lot of flack for that. So I'll turn things over to Paul. Good transition.
Okay, so you can see and hear me now, I guess. So I wanted to pick up on the theme that Mike mentioned about something that was really uniquely characteristic of the Colorado neural networks work, in the extent it was heavily engaged with cognitive science and supported by ICS. And I want to take this opportunity to thank the department, thank ICS for making it possible for me to have an academic career at all by being willing to hire somebody who did not have a degree in computer science, was anxious about the fact that he couldn't probably pass the preliminary exams if he had to, but found that at Colorado in both ICS and computer science, I was made very welcome and very much at home, and it was a very, very fruitful environment to work in. And for that, I will always be grateful. So as Mike mentioned, in our research group, we did work on problems in psychology, explaining phenomena in human visual perception was one of the fields that Mike contributed heavily to. There was work on linguistics, symbolic theories of grammar, in fact, that arose out of neural computing for language. And work in philosophy concerning the problem of compositionality, providing a general solution to how to get compositionality into neural networks. This was through a device called tensor product representations, which will be mentioned once or twice again. But I want to elaborate on what I mean by compositionality and why it's so important. Compositional representations support compositional processing and yield compositional generalization. Compositional generalization is something that's profoundly important in cognition, but very challenging to achieve with neural computing. So let me explain what I mean by these various terms. So compositional representations you're all very familiar with from all sorts of symbolic systems of expressions like algebra, arithmetic, or trees for parsing natural language. And these support compositional processing in the way that's very familiar in computer science. So we can take this constituent, evaluate it, pass the results to bigger constituents, again, can be evaluated, and so on. That's compositional processing. And the same thing is possible with language. Now we're translating into meaning representation using, say, the lambda calculus. And I'm going to skip all the gory details and just say that the same thing happens, but now we're building a symbolic expression of meaning rather than evaluating a number. And what I mean by saying that this yields compositional generalization is that knowing how to do this means we can evaluate any well-formed algebraic expression. We can take expressions we've never seen before and break them down and see them as compositions of familiar parts that we have seen before and that we know how to process. And the same thing is true here. We can interpret any grammatical sentence using this compositional processing mechanism. So that's very powerful compositional generalization. And as I say, that's something that neural networks are struggling to master. So let me drill down a little bit onto language, which is really the area that I work in. Compositional representations have always been crucial in formal studies of language, going back thousands of years. But neural networks have been remarkably successful in language processing in the last several years, especially. They've achieved amazing successes. And that either means that the neural nets don't have compositional representations. They just have these vector representations of activations over neurons. But that, in fact, compositional representations are not crucial for doing language processing well, which contradicts all prior work for thousands of years on language. Or they do have compositional representations, despite all appearances to the contrary. Now, which of these is really most important? I don't know yet. We don't know yet. Both are at work for sure. For example, we know that if you take a very compositional function to teach a network, even a simple plain neural network, if you give it enough data showing all the compositional possibilities, then it actually learns to make its own internal representations that have compositional structure. They, in fact, turn out to be TPRs, the solution to how to embed compositional structure in neural networks that I mentioned earlier. So it's possible for networks to discover this, but they have to be given a lot of data to do it. Now, in recent years, the big burst of success has largely been due to the transformer architecture. And I'm not going to dwell on the aspects of this architecture. The important point for now is that it provides material with which the network can learn compositional representations. Essentially, what the machine can do is, for any given input string of symbols, it can build a graph for data flow that's appropriate for that input to direct the information flow in a dynamic way. And that is that graph is a kind of compositional representation which has afforded quite a lot of additional power. I said that compositional representations have always been crucial for formal studies of language, but discrete structures have almost always proved to be too limiting. So compositional representations are important, but if you realize them discretely, you run into a lot of limitations. So what this provides is an opportunity for neural networks now to be doing compositional representations that are not discrete. So to pop up a little bit, what we can take from cognitive science here is that language and lots of other cognitive capacities require representations that are continuous vectors. We've learned that from the power of vectors in even in language processing, where things seem more symbolic than anything else. And we need compositional structures to get good compositional generalization. So if we take that as a set of principles from cognitive science to try to use to govern our AI construction, then one thing you can do is to have a neural component that provides you the continuous vectors, the symbolic component that provides you symbolic discrete compositional structures. These are kind of hybrid systems that is one part of the field that is now very well studied in many different ways, neurosymbolic computation. You can think about a sort of prototypical case as a symbolic program in which some of the internal functions are not computed by symbolic computation, they're computed by a neural network. If you're interested in hearing more about this, the plenary address by Henry Kautz at the most recent AAAI conference was devoted entirely to neurosymbolic computation and laying out the space of different ways that it's being pursued in the field. Another approach, though, is to have one type of representation that is simultaneously continuous and compositional. That's neurocompositional computation, where the vectors themselves have a kind of internal compositional structure that's appropriate for vector space relationships as opposed to discrete space. Transformers exemplify this to a limited degree, and I think that a lot of the power results from that fact. Another kind of neurosymbolic system is a graph network, where you have a graph, a discrete structure. The structure is discrete, but at the nodes you have vectors that encode information that gets communicated along the edges. This is very well suited to working in formal domains that have discrete structure exactly, such as computer programs. So program synthesis, many games have this property, and a lot of progress has been made by hooking together discrete and structure with continuous content. But this other approach, the neurocompositional approach, makes not just the content, but the structure as well continuous, which makes it suitable for non-formal domains like language, where hopefully you can overcome the limitations that discrete compositional structures have always carried with them for the study of language and conceptual knowledge in many other fields. So why is this notion of continuous structure particularly promising? Well, we have learned about the tremendous power of vector representations. The whole burst of success in natural language processing was kicked off when people stopped using symbols to represent words and started using vectors to represent words and sentences and many, many other things now. So that has proved enormously powerful. And so the idea is to apply this to structure itself, where structural relations are no longer discrete either, but they are vectors in a continuous space. And what this can allow neural networks to do is to have deep learning invent its own kinds of compositional representations and processes, which will of course be continuous compositional representations because it's all done within neural computation. So that was just a glimpse of some of the current trends in natural language processing viewed from a cognitive science perspective as appropriate for a celebration of Colorado's neural network history. So I will pass it back to you, Mike. Oh, I'm not hearing you.
I'm now unmuted. Sorry, thank you. I will share one slide just to kind of wrap up this part of our segment on some of the ideas I think are very important in addition to the ones Paul talked about. I'm not going to go into presenter mode if you don't mind. You'll just see my slide with all the messiness. Let's see. How's that?
Looks good.
Okay, cool. I tried to make a catalog of special sauce, and it definitely includes the material that Paul presented. I wanted to mention a few other things too. Modern neural nets are massively over-parameterized systems. There's many more weights than there are examples, and you can load a neural network with arbitrary training sets. You can change the labels on an image classification task, and it will memorize those labels just fine. And we always used to believe that when models have that much flexibility, you could never generalize well. And so the classic view, this slide that everyone had in a machine learning course, is as you make your model more complicated, as you have more units or hidden layers or parameters, the model training error drops, and you build a model that learns a training set better. But at some point, the test performance goes back up because the model starts to memorize the training data and it doesn't learn regularities in the data. And this is the belief that is sort of the classic statistical view, and the version of this that's emerging both through theory and empirical studies is that there is this weird point where test error does rise, but then it drops back down as you train a network. So not only is it correct, but it memorizes every little thing in the training set. And it's partly a function of the way neural nets are trained, and there's certain conditions under which it happens, and this is a developing area, but it's really what has enabled the kind of models that are producing the kind of very public successes. These are gigantic models that are much larger than the data sets they're trained on, even though the data sets themselves are very large. There's a number of tricks that have emerged over the years that sometimes make a difference, sometimes don't. Batch norm would be probably my favorite trick that I hate, that really does seem to condition deep networks. And then the rest of this list are just particular ideas that seem pretty important that I believe will stand the test of time. So Paul mentioned transformers that depend on this query key attention mechanism, and it's useful not only for language models, but visual reasoning and doing temporal credit assignment. There's generative adversarial networks that can create very lifelike images that everyone's probably seen in the popular press. Paul mentioned graph neural nets for doing causal and structured reasoning, and normalizing flows, another scheme for doing invertible generative models. So that would be my list of stuff that's going on in the field right now that people should pay attention to. And if I've forgotten things, folks should chime up in the chat. Would like to hear what you think. So I'll turn it back to Tammy then.
All right, thank you, Mike and Paul. We have some questions that we collected during registration and some questions that have been coming in through the chat and the Q&A. So Mike, here's one for you. Please discuss explainable neural networks. If a law is passed that a neural network decisions are to be explainable, how can we get there?
So I'm going to answer this question more as a psychologist than a machine learning person. What explainable means to humans is that there's a story you can understand. If people are asked to explain their own behavior, they make up a story. And we know that because there are these beautiful psychological experiments showing that factors that you think are influencing your behavior and your decisions really aren't, and factors that you would never believe have influenced you are actually very important in your decision making, statistically speaking. So what we really want in an explanation is something that we feel we kind of grok the meaning of. And to my mind, that means the way to do explainable AI is not to open up the networks and understand every last weight in the network, but to come up with a good story, to build networks that tell stories about other networks. And that's basically what goes on in our brain. The sort of the decision-making apparatus in our brains is separate from the storytelling apparatus that observes the I/O behavior of our actual decision-making, and then comes up with a story about it. And we're pretty good at telling those stories because we have so many years of experience watching our own behavior. But again, there are limitations to what sort of introspective access we have. I was chatting with Paul about this earlier, and he pointed out the really important factor here is that these explanations aren't causal in nature. There's a separation between the explanation and the actual behavior. And that reminded me very much of work Paul had done in the 80s. He has a very famous paper called On the Proper Treatment of Connectionism that talks about different levels. There's this sort of sub-symbolic or neural level and the symbolic level. And we understand symbolic stories. Symbolic stories are like linguistic stories and express things in these discrete elements and their relationships. Whereas the neural net goop is all, no one can figure out what's going on there. And Paul's argument in that is that symbolic stories or symbolic models are an approximation to what a neural net is doing. A neural net can do these very subtle behaviors through the continuous computation, continuous weights. And you can abstract that away to a symbolic story that captures some of the behavior of the neural network, but it doesn't capture all of it. And it's really that sort of symbolic, sub-symbolic distinction that I think will lead to good explanations. But in order for that to happen, we need to be able to appreciate that the two don't have to be causally linked, and we have to accept that. Can I ask Bobby to jump in? Because he had also, as an ACM president, has had to deal with issues in AI and sort of philosophical things like this. Bobby, are you out there?
You're muted, Bobby.
I was going to say I am, but I have no business answering questions like this when you and Paul are around. Just two quick ones. We're starting to see deep learning algorithms used in ways that are coming up in courts. And there, what the courts are interested in is something maybe more mundane than the discussion we were just having, which is there an algorithm here that they can explain so that they know how you got from point A to point B and can defend whether it's okay or not? So there's a legal aspect to explainable AI. There's something at the other end of the spectrum where people think that, oh, if it can take all this input and come out with this output, the things in the middle must mirror all the things that go on in the human brain. And so people are wondering if there's any truth to that, which you two guys can comment. I'm not aware that anybody's ever shown that's the case yet.
And in fact, Bobby, one of our questions is how much closer has deep learning of the past 2 decades brought us to understanding human cognition or general AI? Any comments, Mike or Paul?
Well, Mike has much more expertise in this area, but there are certainly people who believe that the internal representations learned by deep neural networks that are doing image processing, that are doing object classification, for example, are the best accounts we currently have of actual internal neural representations for visual object recognition as well. So I don't know if you buy that, Mike, but that's certainly been advocated by people who compare the success with other models that have been around longer for generating what we thought were the important visual features or whatever, and the neural nets just blow them out of the water for explaining the neural data.
For vision only.
Yeah, and I think that's really important, Tammy, because the limitation of current neural networks is they tend to be a single system end to end. And what we really need to model human cognition are cognitive architectures and think about interacting components. And I see that as a trend in where the field is headed, at least by people I work with. But it definitely, I think there's an appreciation. We need to build larger models that are doing multiple tasks and have multiple sorts of expertise, not just perception, but perception and language. And when we build these more complex articulated systems that have different modules that are doing these different functions, there seems like more hope of matching that to human cognition in all its richness, not just what happens in the first 200 milliseconds of vision.
And so, Mike, how does, in your mind, how does that relate or not relate to a lot of what we're seeing in terms of multimodal modeling?
Definitely to the extent that you benefit from multiple modalities and multiple signals at once. I can give you one, for instance of that, how it can change our views of what's being computed. So every object recognition model right now takes 2D images and maps it to labels or does scene segmentation. There's no acknowledgement that the world out there is three-dimensional. And if you look at our brains, very early in the first couple hundred milliseconds, we extract information at least about what's in front of what's occluding what. A lot of the Gestalt phenomena have to do with this sort of segmenting the world and into depth planes. And a hypothesis I think is worth exploring, and we're starting to explore, is whether adding depth to models, like sort of before it starts to do vision, if we have a little module that just recovers depth from 2D images, is that going to help various visual tasks? And the evidence we have so far is that it does. So that's one very simple example of sort of, it's not multiple modalities, but it's extracting information of one type and integrating it with RGB pixels, which are the things everyone else uses for vision.
Thank you.
I think that one, sorry?
I said go.
I thought an interesting aspect of what you just asked about and what Mike had said about the need to go beyond models that are very focused on one task, especially one modality, is that the Holy Grail of machine learning is to learn the really abstract concepts and relationships that cognition makes so much use of. And if a system has to generate representations that are going to serve visual purposes and linguistic purposes and reasoning purposes, then I think the pressures for those representations to find the more abstract structure out there that is amodal is greater. And so it may be a necessary step on the roads to more general intelligence and more general purpose knowledge acquisition.
Paul, thank you for that. We have a somewhat related question for you. It appears that current neural net architectures are still not capable of common sense and imagination processes. So what work is going on currently to think outside the box and understand and model these types of cognitive processes?
I'm not sure that I have anything very pointed to say about that. I do think that Mike mentioned the visual, the drawings, the visual art that has been produced by generative adversarial networks, GANs. And when I look at them, I think, wow, that's great imagination. The way that all these different aspects of recognizable parts of the visual world have been woven into this tapestry is really quite stunning. So that's a kind of creativity. It could be that if we applied, maybe Mike knows about this, you did work on this, I know, long ago, whether if GANs were applied to learning about music instead of visual images, maybe you would see some equally creative compositions emerging from them. That's something that's waiting to be done if it hasn't already been done.
Yeah, if it hasn't been done, it'll be on archive next week, I suspect. Paul, I wanted your reaction. Have you seen OpenAI's DALL-E? And I'll share the screen with folks just so people can see some of these images if they haven't. But what's interesting about DALL-E is that it takes a textual description and generates images. So it is doing the kind of multimodal integration Paul mentioned. And it sure feels like it's much more interesting than image classification system. So here it's told an armchair in the shape of an avocado and it generates this, or a storefront that has the word OpenAI written on it. These are the outputs. What do you think, Paul?
Well, I think Isaiah would like some of those chairs.
I would like some of them. Well, I'm always speechless when I see what GPT-3 does. And this is another order of sophistication beyond just generating stories. And I'm just speechless. I don't know what to say. It's just astounding.
Yeah, the number of times I see results and I'm speechless as well. You know, stuff I never thought I'd see in my lifetime. It's cool. I'm not sure how to stop sharing.
Oh, you're stopped, Mike.
Okay.
Yeah. So we have a lot of questions basically around applications and impact. So Mike and Paul, what do you see as the biggest obstacles in the next decade to the widespread use of deep learning?
Well, I mean, I guess it's a little bit glib, but I would say the biggest obstacle is artificial stupidity. I mean, these networks that, for example, GPT-3, which you start a story and it just takes off with it and generates all sorts of lovely English and colorful language and very fluent. And you get the impression that surely there's some understanding of the story that you set up and the story that it was continuing. And then it starts saying things that reveal it can't possibly know what the hell it's talking about. No way can it. And so basically, these are like idiot savants that, and they're also exploiting our ability to project intelligence into systems that don't have it. And so I think that the biggest problem is overestimating the knowledge that these systems have and just trusting them, or not even trusting them, just asking them to do things that are just way out of their league. That's my perspective.
I have nothing to add to that. That's exactly what I would have said. Not as well.
We have a lot of graduate students in the audience today, and they are asking for your advice. So what advice do you have for current students who want to pursue a career in machine learning?
My advice is math, math, math. I saw Jim Curry is in the audience, applied math professor, I guess now computer science. I'm not sure what's happened since I left. We got lucky. But yeah, the more math you have, the better. Statistics, linear algebra. Paul's a physicist by training. That situated him really well. I'm a dopey psychologist by training. It situated me really poorly.
Au contraire. Au contraire, I would compliment your advice, which I thoroughly endorse, by saying that at the same time, people should not neglect a number of areas that you and I both benefited a lot from having studied. psychology, physics in a sort of indirect way, but linguistics in a more direct way. You know, even just not limiting your horizons to what came out on archive since 2020 is already a step that takes you way beyond most people. So, you know, so many of the ideas that really have taken off in the deep learning era were ideas that were developed in the 80s and 90s. You should look at those things. You should read those papers because there's a treasure trove of ideas there that are waiting to be given the big boost that current computational and data resources allow. But I would go further than that. I mean, if you're interested in doing language processing, I think you should study linguistics. I mean, there are many people who have said that, well, every time we try to put linguistics into natural language processing NLP systems, it deteriorates the performance. Linguistics is now dead. And there's certainly some truth to that. But I think that the job of linguistics has shifted now. It's for getting us to understand how GPT-3 can possibly be doing what the hell it's doing. I mean, it's stupid, but it's fluent. How can it be that good at the just syntactic, lexical knowledge of language? And I think we need the insights about language that linguists have and the theories that we can bring to bear to now move to an era of understanding what these models can do. And in the process, we're going to learn a lot about language we didn't know and a lot about what linguistic theory needs to morph into, led by these new models that do things differently than we've ever thought was possible. So that's just one example where I think that beyond the math, which is absolutely the foundation of everything, beyond that, there are important aspects of cognitive science that are going to make a huge difference in the future. And so you should expose yourself to them as well.
I want to underline that in the future part. I think in the short term, if your job is to go out next month and get a job at some sweet spot in industry, it's hard to find folks who have an appreciation for cognitive science. I completely agree with Paul in the long term that that's what's going to make the field successful. That's what's going to lead to general AI. And Paul has it as his mission to bring linguistic theory to MSR. I have it as my mission to bring psychological data and experimental work to Google. And you can ask us in a few years how successful we've been in winning over our colleagues. I was going to mention
that was well worded, Mike. Don't ask us now how it's going.
I was going to mention one other thing in answer to the question Tammy asked, which is at CU, there's many really great opportunities to do machine learning applications. So folks who aren't trying to develop new machine learning methods, new forms of inductive bias, understanding operation of models and why they learn, but rather just have really interesting problems. And a lot of times you come up with new ideas about machine learning from the problem domain perspective. So don't underestimate the value of hooking up with professors who have problems they want to solve and need a young, energetic person to go off and learn TensorFlow and download the right pre-trained model to play with.
Absolutely. Well, you both set up our next question very, very well. It is about cognitive science itself. In the early to mid 80s, there was a debate about whether cognitive science should become its own department-based discipline in a university settings that trains students, or whether cognitive science was better suited as institutes that serve multiple departments. UC San Diego went the department route and Colorado went the institute route. With nearly 40 years of hindsight, what did the different models yield?
Paul was chair of a cognitive science department, so I will let him answer.
Well, I do believe, and I guess I'm just invested in being in a cognitive science department and having put a lot of work into trying to build a cognitive science program that creates true cognitive scientists at the end, that calls for a department. I do believe, though, that the cross-fertilization between disciplines is sufficiently fertile that cross-department institutes can benefit the research that's done in the different departments a lot. So the psychology you do is better if you also are learning about artificial intelligence, and the linguistics you do is better if you're learning about natural language processing. And so I think that the sort of links between disciplines can carry a lot of very constructive information flow. So the result may not be producing graduate students who now become cognitive scientists in my sense of the word, but they're multidisciplinary scientists within the cognitive sciences. And I think there's an important role to be played by both of those models. So that's a non-answer.
Well done, Paul. So we only have 2 minutes. Do either of you have any parting comments to add to our audience?
Well, sometimes I think about it this way. In cognitive science, we have different types of intelligent systems that we've studied. We study adults, we study brain damaged adults, we study infants, some of us study animals, and these are all wonderful cognitive systems to enrich our theory of cognition in the large. And now we have a new one. We have these AI systems, and we can study them as cognitive scientists. It's a kind of a once in a many lifetimes event when a new kind of cognition appears. And there's a lot of artificial stupidity in there, but there's also a lot of cognition in there. And we need to sort that out and figure it out. And I think that's a really exciting time. So that's one way of thinking about it.
Mike, your parting thoughts?
I guess I want to echo what Paul said in the sense that it's nice to have people out there who reflect on networks and really care about what's going on inside of them and don't treat them like black boxes where you download a software package and run the tool. And I'm worried about folks who are too trusting, who just apply these things sort of willy-nilly without really doing the reality check as to whether they're behaving the way we want and whether you can construct a toy data set that you know exactly what the right answer is, and your model better be doing that. So I encourage especially students to be more reflective of the systems they're applying.
Skeptical users. So thank you both very much. We're receiving a lot of appreciation and love for the great hour we just spent together. I'll hand it back to Bobby.
And this is a time when it's really sad to be virtual, because otherwise we would have thunderous applause. So instead we just have thunderous virtual applause. But thank you all so much. Thanks everybody for joining us. We had about 300 people joining us, and I just want to let you know a couple things. We will have a second event of this type on April 22nd, featuring Professors Gerhard Fischer and Clayton Lewis, doing a somewhat analogous talk about the growth of HCI in its past, present, and future. And all of you will be getting an announcement of that very soon. There will be a recording of this webinar, and you'll get a link to that as soon as it's available as well. And finally, we've announced recently that computer science has set up an endowed scholarship fund to support future students in honor of founding faculty such as Paul and Mike. So if anybody wants to help with that, you'll get information about that as well. So Tammy, Paul, Mike, thank you so much. This is, you can't pay enough for something like you just did for the last hour. It was wonderful, and thank you.
Thank you very much.
All.